Hello and welcome back to Chemistry Practice. Today we're going to have an introduction into gas laws. First, let's go over three different states of matter. Here we have a solid, liquid, and a gas. The first thing to understand is that in a solid, all of these separate molecules or atoms are very closely packed, which means they really don't move around. They're normally in a crystalline lattice and they can't move. And also, the intermolecular forces between these molecules is very strong, keeping them together. So it has a rigid sort of fixed shape and volume. These do have some kinetic energy, so every single molecule vibrates a little bit, but it doesn't have enough energy to move around. Now, if I look over at liquid, let's pretend we put some more energy into this solid. Notice how these separate little molecules have now broken up. They're farther away from each other. The intermolecular forces are now less powerful, and there's more energy in this system. One thing to understand about a liquid is it's not rigid. You can pour it from one container into another container. And also, it doesn't really have a fixed shape. It just sort of takes the shape of whatever container you pour it into. It also has no fixed volume. It has a fixed volume. So for instance, if I have a glass and I pour water in it, my volume is right here. Let's take another glass and I have more liquid, more water. My volume is higher. See how the volume doesn't fill the container. So it does have a fixed volume. That's different than gas. Gas, the particles are very far apart. And if I put gas in a closed container, these particles will fill up the entire container. They will disperse into this container to fill the whole thing up. So they're zooming around inside of whatever container you put them in. That's what no fixed volume means. It also, of course, has no shape because, just like liquid, it takes the shape of the container it's in. The intermolecular forces between these particles are basically almost zero. We'll talk more about that later. The kinetic energy inside of here is much stronger than liquid or a solid. So that's sort of what we're talking about when we're talking about a gas. And normally we're talking about a gas inside of some container, because otherwise it would just sort of float out into the atmosphere and be everywhere. When we look at gas, we look at three basic things: pressure, temperature, and volume. There are different units for these three different things. So for pressure, as you can see, there's a lot of different types of methods of measuring pressure. One of the most common is called the atmosphere. Standard pressure is 1 atmosphere. 1 atmosphere is the sort of pressure that you would feel on you at sea level in the earth. So we don't think about it, but we actually have pressure pressing on us all the time because of all of the molecules in the atmosphere around us. Now think about it. If you go to Mars, the atmosphere is thinner there, so the pressure would be different. Now if I go up a mountain, the pressure will go down because the atmosphere is thinner up here. If I go to the bottom of the ocean, the atmospheres will increase because there's more pressure down there. Torrs and milligrams of mercury are equivalent. Back in the day, people would have a little container full of mercury, liquid, and then you would put a glass tube in here. When pressure was greater, the mercury went up this glass tube, and then you could measure where the mercury was on this glass tube. So 1 atmosphere equals 760 millimeters of mercury. 760 millimeters of mercury also equals 760 torr. So torr is the same thing, they just changed the name. Kilopascals, another method of measuring pressure. 1 atmosphere equals 101.3 kPa. So 760 millimeters of mercury and 760 torr would be equivalent to 101.3 kilopascals. You're going to see all of these different pressures and sample problems. Temperature, normally we have Celsius and Kelvin. Just remember, if I want to convert from Kelvin to Celsius or from Celsius to Kelvin, I have to add or subtract 273, more or less. So if I have 25 Celsius, if I want Kelvin, I'd have to add plus 273. If I have Kelvin, I have to subtract 273 to whatever my Kelvin number is to get Celsius. Volume, we have liters, that's the most common volume you'll see, but we also have this is decimeters cubed. All that means is I have a decimeter, decimeter, decimeter. So this would be a box, so that is a volume. That would be a volume of 1 decimeter cubed. 1 decimeter cubed equals 1 liter. You're going to be using these units quite a bit, so you should get familiar with them and know how to convert back and forth. Let's go to the first gas law that we're going to talk about. It's called Boyle's law. Boyle's law says if I have some gas at a certain pressure and volume, the pressure and volume have an inverse relationship. So I'm going to put pressure 1, pressure 2, volume 1, volume 2. What this means is, let's say I have a container of gas at, let's just say 1 atmosphere, and the volume is 1 liter. If I increase the pressure, say I make the pressure go up, I'm putting pressure on this, increasing the pressure, the volume will decrease. Think about it. If I'm increasing the pressure, this thing is going, the gas in here is compressible. It'll get squished down. I'm squishing down on the gas. Okay, well, what if I increase the volume? If I increase the volume, the pressure must decrease. So that's all an inverse relationship means. It means there's this relationship between pressure and volume. If I increase one, I'm going to have to decrease the other. Using this law, we can solve basic problems. Our first question says a container holds 500 milliliters of carbon dioxide at 20 degrees Celsius and 742 torr. What will be the volume of the carbon dioxide if the pressure is increased to 795 torr? Well, we will use Boyle's law. Pressure times volume equals pressure times volume. Let's get our first pressure, 742 torrs. Our first volume is 500 milliliters equals our second pressure is 795 torrs. And we don't know what the second volume is. That's what we want to find. Now, this 20 degrees doesn't matter because basically the 20 degrees is the same before and after. So it's constant. Now, I know this seems very simple, but we have to get the V on one side of this equation to isolate it to solve. I understand this is basic algebra, but we should never assume that people know how to rearrange these equations. So how do I get the V on one side? Isolate it on one side. Well, if I multiply both sides by 1 over 795, this will cancel out, And essentially, I will get this over 795. So volume equals volume equals 742 times 500 divided by 795. If I do that math, I will get 466 milliliters, and that is my answer. Let's go down to the second example. A gas tank holds 2,785 liters of propane at 830 millimeters of mercury. What is the volume of the propane at standard pressure? So yet again, we will get our equation. I always just write the equation out so I can see what I'm doing. I need the pressure. The pressure is 830 millimeters of mercury times 2,785 liters equals, and it says what is the volume of the propane at standard pressure? Well, what is standard pressure? Remember how I told you standard pressure was 1 atmosphere? Well, 1 atmosphere is equal to 760 torr. So I need to convert this to 760. And now I need volume yet again. So basically, if I move the 760 over here and just divide, I can find my answer. Volume equals 2,785 times 830 divided by 760. And if I do that, I will get 3,041 liters. And that's my answer. Okay, moving down to the last example of Boyle's law. A balloon contains 7.2 liters of helium. The pressure is reduced to 2 atmospheres, and the balloon expands to occupy a volume of 25.1 liters. What was the initial pressure exerted on the balloon? So I don't know the pressure here. Sometimes being able to solve these problems is more about being able to read the problem and understand what they're asking. So 7.2 liters the pressure is reduced to 2 atmospheres. Here's the pressure, 2. And the balloon expands to occupy a volume of 25.1 liters. So my pressure is going to equal 2 times 25.1 divided by 7.2. And if I do that math, I will get 6.97, which is my answer. Okay, that's as simple as it gets. That's Boyle's law. Now let's go down to a second law. You'll notice that there's quite a few gas laws. This second law is called Charles' law. Charles' law essentially says there's a relationship between volume and temperature. And if I have volume and temperature and let's say I heat something, let me get a little gas container here, and I have a certain volume of gas. Say I have gas in here, and I put a little flame down here. What happens, let's say I had a can of, if you ever had a can of spray paint, it has gas inside of it under pressure. The paint is a gas under pressure. I start heating it. What's going to happen? That gas is going to expand. The volume is increasing. It's getting bigger. So if the heat goes up, if the temperature goes up, the volume must also go up. If the heat is increasing, the volume is increasing. If the heat decreases, the volume decreases. So I have V1, T1, sorry, V2, T2. That is Charles' law. That is the equation, the relationship between volume and temperature. Now, we should always try to put our temperature in Kelvin. We should convert to Kelvin. This will make our life easier because Kelvin has an absolute scale. Kelvin goes from 0 up, whereas Celsius will have negative numbers, and that's not going to work. So, let's see what they're asking here. A container holds 50 milliliters, so our volume is 50 milliliters of nitrogen at 25 degrees. Now remember, how do I convert this to Kelvin? I add 273. So 273 plus 25, we have 298 Kelvin equals my second volume. What will be its volume if the temperature increases by 35? So I don't know the volume here. And this is a little tricky here. It just says if the temperature increases by 35. Okay, well they're trying to be a little tricky here. That's what they like to do in chemistry. Well, if my initial temperature was 25, if I increase it by 35, my temperature should be 60 degrees. Okay, but I need now to convert this to Kelvin. So 60 plus 273. 333 Kelvin. Now I need to rearrange this equation to get V on one side. Yet again with a little bit of math. On this side, if I multiply 333 over 1, so this will cancel. And this side will be 333 over 1. I'll just rewrite it like this. My volume will equal 333 times 50.0 milliliters divided by 298. And if I do that math, I will get 55.8 milliliters. Now you're probably thinking, what about this temperature? Well, remember, that was the temperature we used to convert to 298, and then we had to add this 35 to this 25 to get the second temperature. So just if that's confusing you. The second thing is, well, why did they even give us the pressure? Well, they do that sometimes in these problems. We don't need the pressure though, because the pressure is the same on both sides. It didn't say that we changed the pressure at all. We're just really looking at volume and temperature. So don't worry about the pressure. Okay, another example of Charles' law. A sample of oxygen occupies a volume, and now we see this new decimeters cubed. That's a new type of volume. What will be the volume of oxygen when the temperature drops? So, a sample of oxygen occupies a volume. Our volume is 160 decimeters cubed at 91 degrees. What's that in Kelvin? 364. Okay. What will be the volume of oxygen when the temperature drops? So we don't know the volume. The temperature is dropping to 0 Celsius. Well, 0 Celsius is 273 Kelvin. So I need volume on one side. I'm going to have to multiply both sides by 273. Volume equals 273 times 160 divided by 364. And I should get the answer of 120 decimeters cubed. Okay, making some progress here. We're starting to feel better about ourselves, I hope. Last example of Charles' law. A sample of hydrogen has an initial temperature of 50. So let's just write our equation first. Volume over temperature equals volume over temperature. Let's convert to Kelvin. 323, so volume over 323 equals. When the temperature is lowered to -5, the volume of hydrogen becomes 212 centimeters cubed. Well, let's convert -5 to Kelvin, 273. So we're essentially saying -5 plus 273. So really we're doing -5 over here. So this should be 268 Kelvin. Here's the tricky thing. Did you notice this? What is the initial volume of the hydrogen in decimeters cubed? But they gave us centimeters cubed. So they're trying to be tricky again. You got to watch out. These questions love to be tricky. So I need to rearrange this. I got volume equals 212 times 323 divided by 268. Now, if I do the math there, I actually get 255 centimeters cubed. But they want the answer in decimeters cubed, so what do I do now? How do I change that? How do I convert that? Well, that can be confusing. Let's think about this. Remember that King Henry doesn't usually drink chocolate milk? Remember how we talked about how we could use this to convert units? This is the unit right here. We have centimeters. So essentially we have centimeters. We have 255 centimeters. We're right here, centimeters cubed. But we want decimeters cubed, which is right here. So how do I get from here to here? Well, remember, my decimal is here. So I got to move this 1, 2, 3. So if I move this 3 places, 1, 2, 3, I'll actually get 0.255 decimeters cubed of H2. That would be my answer. Now, if you put this centimeters cubed down, you might get it wrong. Your teacher might mark that wrong because you didn't put it in the right unit. So yet again, in chemistry, be aware of the small little details. Read the problem a couple of times, write down the equation, and then plan your attack. Understand what you need before you start just writing things down and trying to do some math. If you do that, you will be successful. Well, I hope that helped you. In the next video, we're going to look at a couple of more gas laws, and then we might have another video after that. So by the time we're done, there will be about 3 or 4 gas law videos, and we will be 100% set on gas laws, and you will ace the test. All right, yet again, if you have any questions, let me know.